Welcome back. Now let us solve our numerical practice paper, 10 GATE style problems on stress, strain and elasticity, worked step by step. Keep a pen and paper ready, pause whenever you need and solve along with me. Let us start. Problem 1. A 25 mm rod carries 75 kilonewtons over a length of 1.5 meters. The cross-sectional area is pi by 4d squared, that is 0.785 4 times 25 squared, 490.87 square millimeters. Normal stress is P over A, 75,000 divided by 490.87, about 152.8 Newton per millimeter squared. The elongation is sigma L over E, which gives about 1.15 millimeters. Problem 2. A single shear lap joint, a 22 mm rivet through 12 mm plates, carrying 40 kilonewtons. The shear area is pi by 4d squared, 380.13 square millimeters, so shear stress is 40,000 over that, about 105.2 Newton per millimeter squared. For bearing, the area is d into t, 22 times 12, 264 square millimeters. So bearing stress is 40,000 over 264, about 151.5. Same load, same rivet, but two different stresses because the areas are different. Problem 3. A 20 mm rivet in double shear carries 50 kilonewtons. In double shear, there are two planes, so the area is 2 times pi by 4d squared, 628.32 square millimeters. Shear stress is 50,000 over that, about 79.6 Newton per millimeter squared. In single shear, the same rivet would give 159.2, so double shear is exactly half. Remember that. Problem 4. A 16 mm rivet through a 10 mm plate with permissible shear 100 and permissible bearing 300 Newton per millimeter squared. The shear capacity is the shear stress times pi by 4d squared, 100 times 201, about 20,100 newtons. The bearing capacity is 300 times d into t, 300 times 160, 48,000 newtons. The safe load is the smaller of the two, about 20.1 kilonewtons, so shear governs. Problem 5. In a tension test, a 20 mm rod over a gauge length of 250 mm carries 63 kilonewtons and stretches 0.25 mm. The area is 314.16 square millimeters, so stress is 63,000 over that, about 200.5 Newton per millimeter squared. Strain is the extension over the gauge length, 0.25 over 250, which is 0.001. So E is stress over strain, about 2 into 10 to the power 5 Newton per millimeter squared, that is 200 gigapascals. Problem 6. A steel bar has a direct stress of 160 Newton per millimeter squared, E2 into 10 to the power 5, length 2.5 meters. By Hooke's law, strain is sigma over E. 160 divided by 2 into 10 to the power 5, which is 0.0008 or 0.08%. The elongation is strain times length, 0.0008 times 2500, which is 2 millimeters. Problem 7. Given E 210 gigapascals and Poisson's ratio 0.3, find G and K. G is E over 2 into 1 plus nu, 210 over 2.6, about 80.8 gigapascals. K is E over 3 into 1 minus 2 nu, 210 over 1.2, which is 175 gigapascals. Problem 8. Given G 80 gigapascals and K 160 gigapascals, find E and nu. E is 9 kg over 3K plus G, that is 9 times 160 times 80, over 480 plus 80, 115,200 over 560, about 205.7 gigapascals. Poisson's ratio is 3K minus 2G over 6K plus 2G, 320 over 1120, about 0.286. Problem 9. A 30 mm bar has a longitudinal strain of 0.0008 with Poisson's ratio 0.3. The lateral strain is minus nu times the longitudinal strain minus 0.3 times 0.0008, which is minus 0.00024. The change in diameter is the lateral strain times the diameter minus 0.00024 times 30, about minus 0.0072 millimeters, a small decrease. Problem 10. A bar carries a uniaxial stress of 100 Newton per millimeter squared with E2 into 10 to the power 5 and Poisson's ratio 0.3. The linear strain is sigma over E, which is 0.0005. The volumetric strain is the strain into 1 minus 2 nu 0.0005 times 0.4, which is 2 into 10 to the power minus 4. And that completes all 10. Score yourself out of 50. 42 and above is excellent. 32 to 41 is good. Below 32, revise once more. You have now solved the full stress, strain and elasticity set, both the MCQ and the numerical papers. Collect the free PDFs and notes on Telegram and subscribe for a brand new lesson every day. Keep it simple, keep it civil.